Welcome to the class again. In the last class we have discussed about the atomic structure and also some fundamental terms of aqueous chemistry. And we have to be in this session we are going to discuss about the properties of the solutions, and I have defined some numbers, some technical terms which we commonly use in all our day to day life and in chemistry also. So, most of the electrochemical techniques are concerned with the reactions of solutions and occasionally in the gaseous state, and most of the solutions contain molecules, atoms, ions, mixtures, etc. Since we will be dealing with solutions, it is better to know about how to express the concentrations of the solutions in various units. Lot of IIT students are asked questions in this area, express the concentration of one particular unit into another concentration units. 99% of the time I see that most of the students fail in converting from one unit into another unit. So, anyway, that is that apart. Since we also have lot of engineers in my course, it is better to recapitulate. Basically, this is all high school stuff only, that is second PU stuff, and let us learn about the definitions. This I have already covered in the last class, but for your benefit I want to quickly do it once again. So, solution is substance which contains a solvent and another component that is dissolved in that is solute. So, we have defined solute and solution. So, solution is in larger quantity, solute is in smaller quantity. So, solution solvent is a major component in a solution and solute would be a minor component. Solutes can be any number, 1, 2, 3, 10, hundreds, maybe thousands, depends. Okay. So, we have solutions of different substances, that is gaseous solutions containing gas, liquid or solids. We can have liquid solutions containing gas or liquid or solid solutes, and we can have solid solutions, that is solid solutions only. They may contain gas. For example, there are a lot of gas sponge metal iron you would have seen with lot of blisters, those things contained gas at one time. So, they are all solid solutions containing gases. They may contain liquids. If you break lot of stones, you will see that there are some stones in which some water would have been held. Lot of our folklores contain stones containing water and water in the stones. So, when the stones break, water comes out, and that is that. We can also have solid solutions. Solids, that is something like alloys and mixtures, alloys and mixture solutions. So, we have expressed concentration. These are the standard terms. One is mass percent of a component, that is mass of the component divided by total mass of the solvent or solution multiplied by 100, and we have volume percent, that is 100 to 100% again it can be told, volume of the component divided by the total volume of the substance. So many ml of a solute in so many ml of the solution, like that. This is a very standard solution. Whenever we say give me coffee, I will say put 5 grams in 100 ml. That is how coffee is made. Put 2 grams in 100 ml. I do not want coffee, I want only a small 0.5 gram, like that. We can express volume component. And then we have mass by volume component, that is mass of the solute dissolved in 100 ml of the solution. Not necessarily 100 ml, but it is denoted by V, whatever is the volume. Then we have parts per million, that is number of parts of component contained in 10 raised to 6 parts of the solvent. that is on number of parts of a component total divided by total number of parts of all components including the solvent. So, that is 10 raised to 6 that is ppm. ppm is also known as microgram per milliliter or milligram per grams per kg. Okay. So, 1000 times smaller than that concentration is parts per billion, that is 10 raised to minus 9. To express substances in parts per billion level, what you should do is take number of parts of component, divide it by total number of other solvents, etc., and multiply it by 10 raised to 9. Then we also have parts per trillion level, that is 1 in 10 raised to 12 this thing, that is known as picograms, picograms per ml, that is 10 raised to minus 12, that is ppt, parts per trillion. We also have femtograms, that is 10 raised to minus 15, etc., but they are not very relevant to our studies in this. Then I have defined mole fraction, that is total number of moles of a component divided by total number of all components. So, if I have x1, x2, x3, etc., substances dissolved in a solvent, I would say that the mole fraction of A is given by Na divided by Na plus Nb plus Nc plus whatever it is, all other components, or I can simply write sigma N1, N1 divided by sigma N1 plus N2 plus N3, like that we can write. Then I have defined what is known as molarity. Molarity is number of moles of solute dissolved in 1 liter of the solution. So, molarity is nothing but atomic weights of the substances in grams and then dissolved in 1 liter. Suppose you want 1 liter, 1 gram, 1 molar sodium chloride. All you have to do is take 23 gram of sodium and 35 grams of chlorine, and then mix them, that is sodium chloride, that makes it 58. So, if you dissolve 58 grams of sodium chloride, you have 1 mole of solution. You should dissolve it in 1 liter. So, the definition goes like this: moles of solute divided by volume of the solution in liters. There is one more parameter, that is molality. That is one is molarity, another is molality. So, LITY. So, molality is defined as moles of the solute, that is same as atomic weights of the substances divided by mass of the solvent in kg. In the molarity we have volume of the solvent in liter. So, mass percentage, mole fraction and molality are all independent of the temperature, whereas molarity and weight by volume are functions of temperature. So, because the solubility keeps on increasing with temperature, sometimes it may decrease also. So, but it is a function of temperature and pressure also. So, what is solubility? Solubility of a substance is defined as the total quantity of the solute dissolved in a unit quantity of the solvent at a given temperature and pressure. You have to specify the time, you have to specify the temperature, you have to specify the pressure, take the solvent and take the solute, say that so much has been dissolved in so many ml of the solvent at this temperature and pressure. So, that is solubility. Now, we have some sort of equilibrium solution, a reaction between dissolved and excess solute present. Sometimes what happens is you keep on you take solvent. I want you to imagine that you have 100 ml of water, you keep on adding sugar into that, it will dissolve, add more sugar, it will dissolve, add more sugar, it will dissolve, until a stage comes when it can dissolve no more sugar. So, that is an equilibrium reaction between the dissolved sugar and undissolved sugar, and the solvent, given amount of solvent, that is at the particular pressure and temperature. Okay. So, this process is known as dissolution. So, some solute particles collide with solvent particles and some solute particles also, and they get separated out of solution. That is what is happening whenever we add extra salts into the solution. That is how it can no more dissolve. So, this process is known as crystallization. So, you prepare a totally saturated solution, just leave it there. Imagine honey in your house. Honey, if you just keep it like that, there will be sugar crystals at the bottom. So, how do they form? Because the water evaporates and solute particles, that is sugar particles, will collide with other sugar particles, will collide with other solvent solutions and then precipitate and crystallize. The process is known as crystallization. Since both these processes occur at all the time, a stage is reached when both these processes occur at the same speed. Otherwise, at some stage it must keep on dissolving, at some stage it must keep on precipitating out. So, I have an equilibrium solution reaction, that is solvent plus solute is a solution, and at a given temperature and pressure, maximum concentration of the solute would be in dynamic equilibrium with the undissolved solute. Such a system is called a saturated solution. So, for all practical purposes, what you should do is keep on adding until it dissolves no more. So, that is a saturated solution. So, data is available in the databases and other places. Google, if you hit what is the solubility, what is the of a sugar, what is the solubility of salt in water, what is the solubility of particular chemical in a solvent, like that lot of database is available. So, an unsaturated solution can dissolve more solute, whereas a saturated solution cannot dissolve anymore. So, a polar substance like sugar, salt, etc., they dissolve in polar solvents, that is water. The most polar solvent what we know in the world is water. So, water is a solvent for many things in the environment. That is why we have water pollution in our hand. Whatever we throw reaches the rivers, reaches the waters, reaches the sea, reaches the well. So, water gets polluted. So, water is being a polar substance, it will dissolve many things. A non-polar solute dissolves in non-polar solvent. So, fundamental rule, polar substances will dissolve in polar solvents, non-polar substances will dissolve in non-polar solvents. Fairly simple to understand. So, we say like dissolves like. Okay. So, many gases also dissolve in solvents. That is also a situation which is very common in our day to day life. Whenever we have acid rain in the environment, we have sulfur dioxide dissolving in rainwater. So, we get acid rain. So, if you get caught in a situation, first time rains in the season, they will bring down all the sulfur dioxide, nitrogen oxides and other things in the form of rain, and if they fall on your skin, you may get irritation. It depends upon the concentration of sulfur dioxide, nitrogen oxides, etc., in the atmosphere. So, many gases also dissolve in the solvents, including water. So, the solubility of a solid in liquid is influenced by chatliers principle. So, what is chatliers principle? If a solution, in general, chatliers principle says that if I have a system, I put I try to change any conditions in a system, the system will react in the opposite way to reduce the impact uh, of the change that we want to induce in the given system. So, you take a ball, press it on one side, other side it will expand. You press this side, it will expand on the other side. That is a very simple way of physically putting, but lot of chemical reactions also, chemical reaction systems, they do react the same way if I try to bring in a change in the reaction conditions. If I increase the temperature, solubility will increase. If I decrease the temperature, solubility will decrease. So, in such a way that the system is unaffected by other things. So, the solubility is influenced by this chatliers principle if this dissolution is endothermic, that is delta H is less than 0, greater than 0. Delta solubility, change in the solubility, heat, change in the heat of the solution is greater than 0. That means it absorbs heat from outside to dissolve, that is known as endothermic. So, if it absorbs heat from outside, the system will cool down. So, you take water, add sugar or salt, it becomes cooler than the room temperature. So, such reactions are known as endothermic, and that also follows the chatliers principle. So, the solubility will increase with increase in temperature. If I increase the temperature, the system should dissolve more. So, if it is exothermic, there are some substances when you dissolve in water, it heats up. You take water, add a few flakes of sodium hydroxide, it gets hot, you can't hold it. Take sulfuric acid, add a little bit of water, it becomes hot. So, they are all exothermic reactions, they give out the heat to the surroundings. So, the glass that is holding the sulfuric acid and water system, it becomes hot. So, such reactions are known as exothermic. Here we say delta H of the solution, change in the enthalpy of the solution is greater than 0. So, the solubility decreases with temperature. So, pressure does not have any significant effect on the solubility of solids and in liquids also to some extent. So, the liquids are highly incompressible and practically remain unaffected by changes in the pressure. So, if there are gases, they do get affected by change in the pressure, but if it is solid or liquid, they do not get affected much. So, many gases dissolve in water. The solubility of the gases increases with increase in the pressure. This we have already seen. So, there is a law that states that, the law known as Henry's law, that states that at constant temperature the solubility of a gas is directly proportional to the partial pressure of the gas present above the surface of the solution. This is a very simple law. What you should remember is, imagine a substance, a beaker containing water and a gas above that. So, the gas will dissolve in water. The solubility of the gas that is dissolves will be proportional to the pressure of the gas that is maintained above. That is what it is, Henry's law is about. Mathematically, we can express it like this, that is P is equal to KH into X. Here KH is a proportionality constant known as Henry's constant, P is the partial pressure of the gas in the vapor phase. So, what is partial pressure? So, this is a concept lot of people do not know. Actually, I want to tell you that partial pressure is, you have number of gases in the atmosphere, the total amount of pressure that you see is the sum of all different gases present. So, the partial pressure of one gas is only the pressure exerted by one particular component of a gaseous mixture. So, in Henry's law, coming back to this, P is the partial pressure of that gas in the vapor phase, that is above the liquid surface, and X is the mole fraction of the gas. So, this law finds several applications in industry and explains some biological phenomena. For example, we put carbon dioxide in soft drinks, soda, scuba divers dissolve a lot of nitrogen in their blood because the partial pressure of nitrogen increases underwater, and in high altitude climbing also we have this partial pressure of the gases atmosphere becomes less. So, they carry their own breathing cylinders, air cylinders, is not it. So, that is about Henry's law. Now, we have what is known as Roush's law. So, we will become more technical now. Roush's law is it reads like this: for a solution of volatile liquids, the partial vapor pressure of each component solution is directly proportional to its mole fraction present in the solution. So, this is something like the other way. So, what is happening here? I have a solution, I have lot of gases in that, in the solution dissolved in that. So, that will also exert pressure, it will be in equilibrium with the pressure with the vapor phase above the liquid surface. So, the partial pressure of each gas in the vapor phase is proportional to how much is there in the liquid phase. That is how Roush's law is present. Mathematically, we can say that first one component P1 is P1 and P2 are the partial pressures of the components in a particular system. So, X1 and X2 and P1 and P1 naught and P2 naught are the vapor pressure of pure components at the same pressure. So, P1 naught is proportional to P1 naught into X1, and P2 naught would be P2 naught 0 into X2. So, here it is there is an error here, it should not be P2 0, P2 naught, here it should be, please make a correction if you are doing here, it should not be P2 naught, it should be P2 only, okay. And here also it should be P1 on the left side, okay. So, I will try to correct that also. And Dalton's law, next comes Dalton's law. This is another high school pre-university syllabus. Dalton's law of partial pressure states that the total pressure over a solution is the sum of the partial pressures of the components of the solution. So, what we have here in Dalton's law, we want to say that I have a system here containing a solution, I have a system here containing a solution, and then there are a lot of gases dissolved in that, and there is corresponding vapor pressure. Above every solution there is vapor pressure of the solvent, we have to live with that. Above the sea there is lot of humidity, is not it? So, wherever there are large water bodies, the atmosphere becomes humid, you do not feel comfortable. So, above every solution, whether it is in a beaker or in a test tube or just lying there, there will be vapor pressure above that. So, suppose you have a system containing a solution containing number of gases, each gas will exert pressure above. The component of the vapor pressure is the sum of each component, that is total pressure is the sum of each component, that is Dalton's law. So, mathematically how do we express? We express P total is equal to P1 plus P2 plus P3 etc., depending upon how we are how many substances have been dissolved. So, look at the slide now. I have put it in the equation form, that is P1 plus P2 plus P3 plus so on etc., and we can combine Henry's law and Dalton's law. We say total pressure is sum of P1 0 plus P2 naught minus P1 naught into x2. So, this this P2 naught, P1 naught, x2 naught I have defined in the previous slide. Okay. So, here I am plotting mole fraction versus pressure, vapor pressure. So, the pressure here is x1, that is pure component of x component, and when it is 100% pure, naturally x2 should be 0, is not it? So, here x2 should be 0. So, it keeps on increasing here. So, I keep on adding x2 to the pure solution of x1, and then it keeps on increasing. When it becomes 0, when x2 becomes 100, x1 becomes 0. So, maximum ratio mole fraction would be 0 to 1 on this case. So, this will be 0.2, 0.6, 0.5, 0.8 like that up to 1. So, here I am plotting vapor pressure versus mole fraction. Okay. So, total pressure P1 is for pure component, it is here, that is P1 naught, and for P2 naught vapor pressure is like this. Okay. So, in between any composition, it would be the sum of this plus this, P1 and P2. So, the total pressure can be represented like this. So, vapor pressure of solids in liquids. So, in a pure liquid, the entire surface is occupied by the molecules of the liquid, is not it? If a non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. That is understood. In the solution, the surface has both solute and solvent molecules. So, molecules thereby the fraction of the surface covered by the solvent molecules gets reduced. Consequently, the number of solvent molecules escaping from the surface will be correspondingly reduced. So, the vapor pressure also gets reduced. This is only an explanation of the previous diagram. Okay. So, Roush's law in general, in its general form, can be stated that for any solution, the partial vapor pressure of each volatile component is directly proportional to its mole fraction. So, suppose I have two solvents, two solutions, it is known as binary solution. Then solvent, let us denote solvent 1 here and solute by 2. So, when the solute is non-volatile, only the solvent molecules are present in the vapor phase, and they contribute to the vapor pressure, because the solute does not have vapor pressure, it is a solid. Solids have very little vapor vapor pressure. So, if the solute is a solid, it will have very less vapor pressure. So, let P1 be the vapor pressure of the solvent, x1 be its mole fraction, P1 naught will be its vapor pressure. Then according to Roush's law, I can say P1 is proportional to x1, and P1 would be equal to x1 and P1 naught multiplication. A very simple mathematics this thing. So, vapor pressure of the pure solvent keeps on increasing as the mole fraction keeps on increasing. When it is 0, vapor pressure is 0. when the solvent is 100%, it will reach up to a maximum. This is the characteristic of each solvent. So, this curve may have different slopes for different solvents. For solvent 1 it may go like this, for solvent 2 it may go like this, for solvent 3 it may go like this, and somewhere. So, the solutions which obey Raoult's law over the entire range of concentrations are known as ideal solutions. Entire range, that is from 0 mole fraction to 1 mole fraction. So, if it obeys Raoult's law, then it is known as ideal solution. Ideal solutions have two important properties. What are they? The enthalpy of mixing of the pure components to form the solution is 0. That means, almost no heat is generated during mixing, and the volume of mixing is also 0. That means, when I take a substance, add a little solute, the temperature does not increase. Okay, that is number 1. Number 2 is the volume of mixing. After sometimes if you add 2 solvents, the volume will increase. Here, if you take a solid and try to dissolve it in liquid, the volume will not increase. So, delta H is equal to 0, delta H of mixing, heat of the mixing is 0, and I have volume, mixing volume, delta heat, change in the mixing volume is also 0 here. Okay. So, this is a very important concept. In pure components, the intermolecular interactions, attractive interactions will be of AA and BB, whereas in binary solutions, in addition to this AA and BB, we have AB type interaction. Molecules of A may react with molecules of B, attractive interaction. So, if the intermolecular attractive forces between AA and BB are nearly equal to that of AB, this leads to the formation of ideal solutions. So, what is the definition of ideal solution now? There is no change in the heat of mixing, whether it is AA or BB or AB. A perfectly ideal solution is rare, but some solutions are rarely ideal in behavior. Solution of N-hexane, N-heptane, bromoethane, chloroethane, benzene and toluene, they all fall into this category. They are rarely ideal in behavior. So, when a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solutions, is not it? If it follows Raoult's law, ideal solution. If it does not follow Raoult's law, non-ideal solution. On what range? It may follow Raoult's law in particular range, but it may not follow the Raoult's law in the whole range of mole fraction, that is 0 to 1. So, in case of, so from the Raoult's law, assume that the figure is like this. Okay. If the vapor pressure is standard, that is AA and BB are all same, and there is no change in the enthalpy or volume delta H mixing, then it is possible that intermolecular attractive forces of AA and BB are weaker than those of A and B. For example, here I have ideal Raoult's law, x1 is equal to 0, here it is x2 is equal to 1, 0, x1 is 1, x2 is 1 here. Okay. So, if it may follow Raoult's law only up to this and then go off like this, or it may follow only go like this and form the go away from the ideality. Ideality is what is drawn at the center. So, the non-ideal, this is known as negative. When it is goes below this curve, it is negative. When it goes above this, it is positive deviation from Raoult's law. Okay. So, in this case, an example of this type is a mixture of phenol and aniline. So, what happens? In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair of electrons on the nitrogen atom is stronger than the respective intermolecular hydrogen bonding between similar molecules. This is slightly more technically put, but what you can say is intermolecular hydrogen bonding between phenol and nitrogen, okay, is greater than the nitrogen of the aniline. So, here we have mixture of if I take chloroform CH3Cl and this is how it is represented, CH3 carbon Cl 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 and the acetone, similarly chloroform and acetone, CH3COCH3 is acetone, okay, and here I have CHCl3. There is some sort of a hydrogen bond between ketonic group and H group and with the negative deviation. So, such molecules will show negative deviation from Raoult's law, that is it will bend towards towards x axis. If it bends towards y axis, then we have a positive deviation. So, this is because chloroform molecule is able to form a hydrogen bond. This molecule CHCl3 will react with CH3COCH3. Actually, this curve should have been here like this. Okay, it should have been this is CH3COCH3, this is CHClCl. There is interaction between these two. Okay. So, here because of this hydrogen bond, there is stronger attraction, and that is why it shows negative deviation from Raoult's law. So, some liquids are there which on mixing form azeotropes, which are binary mixtures having same composition and in liquid and vapor phase. So, substances which have got same composition, in the liquid form mixture and vapor pressure same composition. So, there is no difference between the pressure expected and pressure calculated composition. You condense the vapor, you will get the same solution, that is such a mixture is known as azeotrope. So, in such cases it is not possible to separate the components by distillation at all. If the vapor pressures are different, then I can heat one component, heat the whole solution, take out one component, because the one with maximum vapor pressure comes out first, then comes second, then comes third, like that. But in the case of azeotropes, vapor also is same and liquid also is same. So, if I condense the vapor, I get the same liquid. So, it is almost impossible to separate the components by fractional distillation, because fractional distillation is a sort of physical separation. There are two types of azeotropes called as minimum boiling azeotrope and maximum boiling azeotrope. So, the solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. So, we will stop here and continue our class in the next session. Thank you.